Bellman's Equations, Part 3. In this video, we shall learn a new concept called the optimal policy, and then we shall see how Bellman's equations can be modified to apply to the optimal situation. So, definitions. We are given state S. The optimal action A star is the action that maximizes the total discounted reward. So the state S is given, and everything optimal we denote with this superscript star. So the optimal action is the action that maximizes the discounted total reward from that state S. And the optimal policy is the policy that gives the optimal action for the state, for each state S. So in other words, pi star is the optimal policy. It's a mapping from each state S to optimal action A star from that state. Some notations. So pi star is the optimal policy, and that's a mapping from states to actions. States here in the argument, and that gives you the optimal action. A star equals pi star S is the optimal action. Now, the value of any state when playing the optimal policy, when applying the optimal policy, is V of pi star S, and we can write it as V star. So V star is the optimal state value. Likewise, the optimal state action value is Q star, which is Q of pi star. Now let's look at it a little further. So we have a state S, which is a board configuration for chess. Now we have one gentleman here who plays a very suboptimal policy pi. It's nowhere close to optimal. He's not a very good chess player. What's the value of this state for him? Let's say the value for this guy is 0.001. This particular state. Why is the value so low? That's because whatever action he'll take based on his policy pi will definitely not lead to a maximum of the total discounted reward. So the expected reward will be quite low, and that's why V pi S is also very low. Now let's look at another guy here. This guy plays the optimal policy pi star. So for him, this board position, given this board position, he can definitely make a very good move. And so he's playing the optimal policy. The value V star S is very high. Maybe it's the highest. It is the highest, in fact, for the optimal policy. So V star is 100 for this same state. And now it makes sense to realize that V star S is always greater than or equal to V pi S. So if you play a policy pi, then the value of the state that you get will always be less than the optimal value of the state when the optimal policy is being played. So this is an important intuitive equation. V star S, the optimal value is always the highest possible value of the state. So in other words, under optimal policy pi star, the state value of each state is maximum. V star S is max pi V pi S for every possible state. And pi star S, given state S, is the optimal action, which is argmax of V pi s. So what action to choose given any state S? We have to choose the action that maximizes the value. Okay, so here is another example. Now we are looking at Q values. Here we have given state S, and there are different possible actions. This action here has a Q value of 3. The optimal policy is being played, by the way, and so it's all Q star. So Q star for this action is 3. Q star for this action, this is some other A, is 11, and Q star for this action is 32. So what's the optimal action? It's this, which maximizes, which has the maximum of the Q star values. So this is A star because it maximizes Q star SA. In other words, A star equals argmax with respect to A of Q star SA. This is again rather intuitive, but it's very important to note this. So the optimal action has maximum state action value. State action value is Q value. So the optimal action A star is the action that has the maximum Q star SA. So pi star, the optimal policy is argmax A of Q star SA. And V star S is the optimal state value that's maximum with respect to the action A of Q star SA. In other words, in the previous example, the optimal value V star was 33 because Q star SA was 33. So now let's write down Bellman's equations for the optimal value and the optimal state action value. V star is V star S, so we are given a state S. What's V star S? We have to take an action A that maximizes the immediate reward plus the discounted future rewards. And this A is the same as this A and this A. So we are taking the maximum of this entire argument. And this entire argument contains probabilities inside here. So these are the probabilities. Q star SA is RSA plus gamma of summation PSA S prime V star S prime. Now, if you notice, we don't have the maximum here. Why not? Because we have to evaluate the Q for every possible action A, not only for the optimal action A. When we replace A with A star, the optimal action, then we get V star SA. So V star S. So V star S is simply the highest of all the Q star SAs. And so here, this is important to note that we don't require the maximum here. It's automatically implicit in this expression because the next state is S prime, and from S prime we assume that we are following the optimal policy. But only for this state S, we are evaluating all the actions. So we are not following only the optimal policy, but we are looking at every possible action. And this gives rise to this. So since we saw that V star S prime is equal to, or rather V star S equals max of Q star SA, so all I have done here is replace S and A with S prime here and A prime here, and so I get this third expression here. And here we do have the max, because now V star S prime we are replacing with max of Q star S prime A prime. Now this is again a very important relationship, because what it has done is it has transferred the max from the outside to inside here. And here when we do the maximization, it's important to note that we do not need the transition probabilities. This is the transition probability. It lies outside the max. So comparison of Bellman's equations for any arbitrary policy pi, what we have, V pi s is R s pi s plus discount times expected value of V pi s prime, where s prime is the next state. Again, for the any arbitrary policy pi, Q pi sa is RSA. Now we are evaluating every action A, so it's not pi s here, this is every action A, so this is equal to RSA plus gamma times expected value of Q pi s prime pi s prime. This Q pi s prime, when you apply the optimal policy, gives you the optimal action. Not optimal, excuse me, I meant when you apply a policy, it gives you the action corresponding to that policy, and this therefore is the same as V pi s prime. Now for the optimal policy pi star, these are what the corresponding equations look like. V star is now max with respect to A of RSA of plus discount times expected value of V star S prime. And likewise, Q star SA is equal to RSA plus gamma times expected value of the max of the Q star for the next state S prime. So these are Bellman's equation. This is for any policy pi, and this is for the optimal policy. Here we have a max for the value function, and we have the max here for the Q value function. Our learning objectives in reinforcement learning are twofold, or are of two types. Policy evaluation. In policy evaluation, we have a policy, maybe a defensive driver when driving in a freeway, or playing a defensive game of tennis. So given a policy pi, find V pi s or Q pi sa. That's policy evaluation. We know the policy, we want to evaluate the what's the value of a state, or what's the value of a state action pair. Policy improvement is when we want to optimize. So we want to find the optimal policy pi star. And we might have to, may or may not have to compute V star and Q star in the process. Depends on the algorithm. Another way to classify our learning is offline learning. It can be applied only in a simulation environment. And online learning is what can be applied in the real world. And this is another important dichotomy, because you'll see the importance of the Q in moving the max operator from outside to inside. That gives rise to this online learning. Otherwise, online learning wouldn't have been possible. We shall see that later. The end.